Centripetal force. Centripetal force is a convenient name for the net force acting on an object moving in a circle. We say it's a convenient name because centripetal force is a force, but it's never listed on a free body diagram. It's always a different type of force acting as the centripetal force. We'll go more into that in just a moment. In the centripetal force, an object that experiences acceleration must have a net force, the centripetal force. So if an object is spinning in a circle and accelerating in a circle, the net force required to keep the object moving in a circle will be pointed towards the center, and it's causing that centripetal acceleration. It's causing a change in direction, even if the object is not necessarily speeding up or slowing down. That centripetal force is acting towards the center and changing the direction of the object. You know that force equals mass times acceleration, but since centripetal acceleration is v squared over r, we can say that centripetal force is mv squared over r, directed towards the center of the circle. So like we just said, the centripetal force is not a new kind of force. It's instead the net force that's due to one or more of our other familiar forces, such as tension, friction, or force normal. So for example, take a look at this dude down here. This dude is spinning a rock in a horizontal circle, and this picture shows that rock paused at just a moment in time. You can see that there is a force acting on the rock, and that force is acting towards the center of the circle. So that is an example of centripetal force. In this case, the centripetal force acting on the rock is the force tension. So the force tension is your centripetal force. Let's try another example. Let's say that you are riding on the gravitron. For me, growing up, this was sometimes called the Starship 2000. It's a carnival ride, and when you walk into the ride, you're placed along this outer carpeted wall, and as the ride starts spinning, the floor drops away and the rider's feet dangle. So if you were going to draw a free body diagram of the rider, you might know that there's a force gravity acting downwards. What's the force acting upwards, and what's the force acting towards the center of the circle? Since this is the surface or the wall, you might realize that it's actually the force normal acting towards the center of the circle, that the force normal is equal to the centripetal force in this example. What's the force acting upwards? That's the force friction. That's what keeps her from sliding down the wall, and that's why the wall is often carpeted. Let's try another example. Here's a motorcycle going around a tight curve. You can see there's a circle in the road, and his net force is acting towards the center. The force acting towards the center, if we were going to draw a free body diagram of him, there would be a gravity, there'd be a force normal, and this would actually be the force friction. So in this example, force friction is acting as our centripetal force. This makes sense because if the road becomes really wet, it gets really slippery, and the chance that you would slide off the road becomes higher because your friction decreases on a slippery road. What force is acting as the centripetal force in the circumstance of the Earth orbiting the sun? That would be the gravity. So in this situation, the force gravity between the Earth and the sun is what's the centripetal force as well. You may have seen that it said that the centripetal force can be the net force. So this is an example of when you might have a net force. It says what force is acting as the centripetal force for a tetherball moving in a circle around the pole. So in drawing the free body diagram for this tetherball, there's a gravitational force acting downwards. There's a tension force acting upwards at an angle, and this tension has two components here and here, with the downwards gravity component being equal to this upwards part of the triangle. So this means that if you were comparing the up, the down, the left, and the right, that the net force acting in this situation is this component of the triangle here to the left. And if you know the angle at this point is equal to the angle at this point, you might say that the centripetal force right here is equal to the force tension times the sine of theta. A weird and cool application of this is in space stations. So you may have noticed that sci-fi movies often have circular shaped space stations. For example, here's Interstellar, 2001: A Space Odyssey, and Elysium. And that's because for people inside of a circularly moving space station, they don't have a normal force of gravity. And you can create the idea of artificial gravity from this centripetal force. So as the object starts to spin, the centripetal force is acting towards the center of the circle, the centripetal force taking place of their force normal. And that's going to create the feeling of weight, the feeling of artificial gravity, because weightlessness occurs when your force normal is missing. So if you can supply that force normal through the spinning motion of the object, you can create artificial gravity in space. Here's an example. It says a level curve on a country road has a radius of 150 meters. What's the maximum velocity at this curve can be safely negotiated on a rainy day when the coefficient of friction between the tires in the car and the road is 0.40. This is the reason why on a highway entrance ramp, there's usually a sign that says speed limit 35 miles per hour when going around this turn or something. So what this is essentially asking is, what speed should you have on a highway entrance sign so that you can safely go around the turn in the rain and your car won't slip off the road? So to solve this problem, you have to remember that here's a car as if you're viewing it from the front, that a car traveling around a circular path, that its centripetal force is the force of friction. It also has a force gravity and a force normal, but the centripetal force is this force friction right here. So we can say force friction is our centripetal force. You might notice that we don't have either the force friction or the force centripetal, which means we're going to have to go one step farther and break this down into force friction, mu times force normal, and set that equal to force centripetal, mass times velocity squared over r. But even at this stage, you might say, hey, we don't know our force normal. But we do know that our force gravity is equal to our force normal. So if we say mu times our force gravity, mass times 9.8, equals mv squared over r. At this point, you might realize that there's a mass on both sides, so you can cancel out the mass and fill in the variables we know and solve for our velocity, which is 24.25 meters per second. So that's the velocity that would be placed on the road sign up here, telling you, hey, the maximum speed at which you can go around this curve is 35 miles per hour. Otherwise, you won't have enough friction to stay on the road and your car will slide into a ditch. Here's a similar problem on a banked road. A banked road is a road that is acting at an angle. It's commonly found on racetracks or other places where a car has to move quickly. On a banked road, the bank in the road itself means that you can go faster. So here's the information given. It says a curve on the racetrack has a radius of 70 meters and an angle of 15 degrees. At what speed can the car take this curve without assistance from friction? So if the friction is 0, that means that we need a different force acting as our force centripetal. You can see here's a top view of a car going around this circular path. And here's a rear view of the car going around the circular path. And that if you were to draw a free body diagram of just this car, there would be a normal force and a weight. And that its free body diagram might look something like this. I'm going to draw my own version below. So here's like a circular path, and here's like the road that it travels on. You can imagine it kind of looking like a funnel. And here's the car as it travels along this like circular path. So since the path is circular in this direction, that must mean that the centripetal force has to be acting inwards towards the center of the circle. And we have to find a force that's acting inward. This car has a force gravity and a force normal, and you might notice that the force that's acting inwards towards the center of the circle is this part of the force normal right here. And that makes sense because the force gravity downwards has to equal this part upwards. So if this angle right here of the hill is 15 degrees, that means that the angle right here is also 15 degrees. We know that this side is equal to our force gravity, so we can call that mass times 9.8. We want to set our centripetal force equal to this part of the triangle right here. I can use my sine, cosine, and tangent to find that value, and I find that that equals to m times 9.8 times the tangent of 15. And I can fill that into my equation over here, and I can set that equal to the centripetal force, and then cancel out both the masses, fill in my radius, and solve for a velocity of 13.56, which is about 30 miles an hour. So that means that a race car on this racetrack can only go about 30 miles an hour before starting to rely on the friction of its wheels to keep it in place. So that's one of the reasons why racetrack cars oftentimes have big frictiony tires, and they only run on nice days with no rain, because then they can have the most friction and they can go faster than 30 miles an hour. Here's a weird and cool thought. When you're walking, your body is in circular motion as you pivot on your forward feet, and your feet move in like a circular path, with the radius of that motion being the length of your leg. That means that your maximum possible walking speed is determined by the length of your leg and the free fall acceleration. So that means that if you have really short legs and you're used to being like, wait for me, I have short legs, that's a legit thing. Your short legs mean that you have a slower walking speed than a longer legged person. This doesn't apply to running, just walking, because in running there's other forces involved. So one question you might have at this point is, why is it that you tell me that the centripetal force points towards the center of an object, but when I spin around in a circle, or I'm going on like a carnival ride, or if I'm driving in a car and I go on a circular path, why do I feel pushed towards the outside? And that apparent weight is called your centrifugal force, which is actually not a force. It's the apparent force that pushes you outwards when you move along a circular path, but it's due to your inertia. It is not a force at all. It's called a force because before we knew exactly what was happening and what forces are, they came up with this name. But this centrifugal force is not a force. It will never be on a free body diagram because it's not a force. And it won't be in Newton's laws because Newton's laws are about forces and it's not a force. But it's called the centrifuge because there's a device called the centrifuge that you can put like blood and other biological materials into, and it spins it super fast and helps separate the particles of like blood or other liquids. And it relies on the same idea. So what happens is that as an object moves in a circle, it has a path of inertia tangent to the circle that's the same as their direction of velocity. And as an object moves, it wants to continue along that path of inertia, but it can't because it's being pulled inwards. And so the intersection of its desired motion and that force creates the feeling of being pushed to the outside. It's not a real force, it's just a feeling. So let's give an example of some of these feelings. The first one happens oftentimes when you're driving in a car. Let's say you're driving in a circular path and you notice that the cell phone next to you slides off the seat in the opposite direction, like this. And you might say, this is a really great example of centrifugal force. But the reason why it's moving in that direction is not because there's an actual force in that direction. It's actually because the object on your seat wants to move this way, but the car is rotating this way. And when the car rotates this way, it's then like facing more in this direction, and it makes it look as though your object is flying outwards, but it's not. It's really just continuing along the path of motion it already had. So it's appearing to move due to centripetal force to the outside of the circle, but actually it's just following the path of its velocity tangent to the circle as a result of the motion and inertia that it already had. The same thing happens if you swing a bucket of water in a circle above your head. You might know, perhaps from experience, that if you were to just hold a bucket above your head, that the water would all spill out and you would get wet. But when the bucket is spinning, there comes a point when the bucket is upside down and the water doesn't come out on your head. So why is that? It's for the same reason. It's because the water at this point wants to travel this way, but it can't because the bucket's in the way. So what happens is that the water sloshes into the bucket like this. And so that every chance that it moves, the bucket is still there. So when it's upside down, the water is like this. And so if you were to slow down the rotation, especially if you were to stop the rotation, yes, the water would slide outwards. But as long as you're moving it at a high enough velocity, the water is going to stay inside the bucket. Another example of this happens as you drive through a dip in the road or along the crest of a road. You're going to feel lighter or heavier than normal. On a crest, you're going to feel lighter. And in a dip, you're going to feel heavier, and that's due to your motion. Remember that the centripetal force is a convenient name for net force acting on an object moving in a circle, which means that this car on the crest of the road is going to have a net force acting downwards. What that means is that the downwards force of gravity has to be larger than the upwards force of normal. And since your force normal is smaller than you're used to, you're going to feel lighter. The same is true at the bottom of the dip. The centripetal force, or net force, is going to be pointing upwards, which means the normal force upwards is larger than the force of gravity downwards, which means that your object is going to feel heavier than normal.